So let's look at what this would be in 2 dimensions. So I'm going to come back and I'm going to start with my single dimensional axis x, and then I'm going to add a second dimension, a second axis, which I'm going to call y. Again, x and y extend forever in either direction. And now I have a 2-dimensional space, whereas in my 1-dimensional space, points can only exist on this line. Here, in my 2-dimensional space, points can exist anywhere in this flat 2-dimensional space. They can't exist above the page or below the page, but they can exist anywhere in this flat plane. Now, you can add as many dimensions as you want. We typically work with 3-dimensional space because that's kind of where we live. The important thing is to remember that as you add each dimension, these dimensions are defined relative to what we call orthogonal vectors. So here you have 2 orthogonal vectors. Orthogonal means simply that the scalar product of the 2 vectors is equal to 0. What that means in 2-dimensional space or 3-dimensional space is that they're at right angles to each other. So we have a right angle here between x and y. So now let's look at a couple of points, and I'm going to take my rigid rod here and put some tick marks just to make this easy. And we'll just assume that all of these are perfectly equidistant. So we have an origin here which has coordinates 0, 0, this being x and y. And so every point in our two-dimensional space now has 2 coordinates, an x coordinate and a y coordinate. For instance, if I pick a point here, which we will again call P, you can see that this point has an x coordinate of 4 and a y coordinate of 3. Now I can choose another point. Let's make him right here. We'll call this our Q. And here we see that he has an x coordinate of 6 and a y coordinate of, let's pretend like that's minus 4. So now I have 2 points in my 2-dimensional space. And I've got the same question as before. What's the distance between these 2 points? Well, just as before, I'm going to draw a line. I'm going to attempt to draw a straight line between those 2 points. And now I want to figure out what that distance is. Well, in 1-dimensional space, it's just the difference between the 2 x coordinates. But here we have x coordinates and y coordinates. So in order to calculate this distance, we need to draw a couple more lines. So we're going to draw one line which is parallel to the y-axis, which means it's perpendicular to the x-axis, and it's going right through the number 4 because that's the coordinate of this point P. Then we're going to draw one from here over to the y-axis, And again, we're going to pretend like that would have hit -4 if I had drawn all this, right? And we're going to define this new point here. We're going to call it S. So X has coordinates of x-axis 4, y-axis -4. So now we have a right triangle. Since x and y are orthogonal, they're at right angles to each other, and this line is parallel to the y line, and this line is parallel to the x-axis, then these two lines are also orthogonal, or also at a 90-degree angle. And we remember from simple geometry that in a right triangle, the length of the hypotenuse is equal to the square root of the squares of sum of the squares of each side. So let me just call this A, B, and C. So we know from geometry that C is equal to the square root of A squared plus B squared. So in our two-dimensional space, in order to find the distance between any 2 points, we need to find the distance in the x direction, which in this case is B, and the distance in the y direction, which in this case is A. Square those two, add them together, and take the square root. So, having scratched out the mistake I just made, I'm going to start over. And so we know that the distance between the 2 points, which is C, is equal to square root of A squared plus B squared. So what is A and what is B? Well, start with B. B is the distance in the x direction between Q and S. So B is equal to D sub QS. And we know from what we just did that that's equal to x of Q minus x of S, which in this case is 6 minus 4 equals 2. A is the same thing, but in the y direction, and we're going between P and S. So the distance between P and S is y sub P minus y sub S, which equals 3 minus 4, which of course is equal to 7. So now I have my A and my B. So C, which is the distance between P and Q, is equal to square root of A squared plus B squared, which is equal to x of Q minus x of S squared plus y sub Q minus y sub S squared, and then we take the square root of all that. But then we notice that the x-coordinate of S, which is 4, is equal to the p-coordinate, or the x-coordinate of P, which is also 4. And we notice that the y-coordinate of S is equal to the y-coordinate of Q. So I can rewrite this as the distance between P and Q is equal to square root of x of Q minus x of P, because those two things are equal, plus y sub Q minus y sub P. So now let's go up one more dimension. Let's go into three-dimensional space. And of course, I'm sure everyone has seen this at some point in their education. But here's x, our vector in this direction. Here's y. Our second dimensional vector, which is at right angles to x. And then we'll add a third vector, z. Now, of course, you have to assume that z is actually sticking up out of the page like this. But we know that z is at right angles to y, and z is also at right angles to x. So, if in three-dimensional space we had a cube, then this would be the z direction, this would be the y direction, and this would be the x direction. And so now, for any point in our three-dimensional space, and I'm going to say I have a point P, and let's say that point P is actually 5 units above the page, and here's my point Q, and it's actually 20 units below the page. Then I can now, just sort of generalizing from what we just did, say that the distance between P and Q is equal to the square root of what? Well, now that we have three dimensions, each point here has three coordinates, not just one, not just the next coordinate, not just two, a y coordinate, but a third one, a z coordinate. So for any point P, we have to give it three coordinates, x, y, and z. And for instance, if this was 3 and this was -4, and we were 5 units above the page, then we would say that the coordinates of P are -4 on the x, +3 on the y, and +5 on the z. So our new equation for distance now becomes x of q minus x of p squared plus y sub q minus y sub p squared plus z sub q minus z sub p squared. And it doesn't matter whether you're talking about distance between p and q or q and p, or whether this is x of p minus x of q or x of q minus x of p, because you're squaring these and you're taking the square root, you always end up with a positive number. Distance is always greater than 0. Okay, so that is our one-dimensional, two-dimensional, and three-dimensional space. For a lot of things, you can get by with one-dimensional space, and that's where we're going to start. But for some things, you need three-dimensional space.